Hello, everyone. Do you hear me? Yeah, even
Yes, we
I
hear
could
you,
hear
Konstantin. Just give us a
myself.
second. So we can get the slideshow up here. That is okay, I think. That's fine.
Thank you, Konstantin. Take it away, please.
Okay. Hello, everyone. My name is Malanchev. I'm postdoc here at Illinois at Gutham's group. I'm deeply sorry that I'm doing it in this old-fashioned Zoom format, not in person. You could guess the reason for this. And please be safe and get tested. Okay, today I will report some results of finding missed ZTF transient by SNAD team. So SNAD team is originally abbreviated from supernovae anomaly detection. So our main work is anomaly detection in different catalogs with different methods. But today I will focus more on our results on finding transients, mainly supernovae missed in ZTF using data releases. Okay, let me go to next slide. So this is a typical pipeline we use in our work. It is not unique at all, but let me use it as some guide over my talk. So I will present different methods of machine learning and a bit different data sets and different results. But everything is started with the light curves from ZTF data releases. Then for machine learning stuff, we do some preprocessing. Today it will be feature extraction. Then we use different machine learning things, for example, anomaly detection or applied detection. Both names work today. Then we have some list of candidates from our machine, which we can analyze. So we do it. So we have good experts in our team to analyze not light curves only, but also metadata, original images, and cross-match catalogs data and doing simulations. I will talk a bit about it later. So then we decide if objects are interesting or not, and if they're interesting, I will report about them today. If they are not interesting, they will live somewhere in a databases and nobody will care about them. So I will go a bit non-linearly through this pipeline because light curves, preprocessing, and results analysis are more or less the same for all papers, all results I will present today. But I will describe different machine learning methods and different results yielded by our analysis. So there will be a pair of slides. There are 3 different methods. And in the end, I will highlight some potentially interesting objects we found and discuss why all these objects could be missed by the community during the time when they should be or were streamed through the alert stream of ZTF. Okay, let's go to ZTF. So thanks yesterday talk by Mark and today's talk by Dan for introducing implicitly and explicitly ZTF survey. So I will not introduce it again. And some of you probably familiar with ZTF alert stream data, what it has and how it looks like, but could be not familiar with the data releases, and they're quite different. So let me highlight these differences to make it more clear. So first of all, photometric pipeline is different. So for data releases, we have apparent photometry, and for alert stream, we have photometry from differential images. We have very different IDs. So all IDs I will show today are belong to, or most of them at least, are belong to data releases. And in data releases, the single source could have dozen of different IDs and dot on different light curves, because we have individual light curve, individual object for each combination of passband and field. The good thing about data that includes ZTF private surveys, including high cadence survey and including some data in I-band, something like 10% of all the data set, which could be useful in analysis at least. Data releases don't have some features of alert stream. They don't have node detections. They don't have some metadata important for this talk. It doesn't provide bogus real score for detections. And the scope of the releases is something like 4 billion. The volume of the last data releases, something like 4 billion light curves and hundreds million detections, billion detections. Sorry. Okay. So we have our light curves from data release. Let's go to preprocessing. For everything I will talk today, we use feature extraction. We found that existing solutions in Python are not fast enough for us because we would like to analyze millions of light curves in bugs. So we developed light curve feature extraction toolbox. In our typical pipeline, a billion light curves, feature extraction from million light curves takes something like a few CPU hours. And you see we have a variety of features, and we use this code a lot and we made it public. You could pip install it, and it is used by at least 3 ZTF LSST brokers. So please install it now or just after the talk and write me angry issues to our GitHub. Okay, the next thing I skip machine learning stuff for a moment, and next thing we use in our analysis is ZTF data release viewer we developed. So it is a better way to analyze light curve data not only from ZTF data releases. So you see, first of all, we do cross match between these different object IDs. So you could see the single light curve here, multi-pass band. You could click on any detection to load ZTF scientific image. It is a bit large, so wait a bit until it loads. So, and we have a lot of complementary data. So we have cross-matching with a lot of catalogs and periodification by periodogram and so on and so on. If you scroll it down, you'll find all cross-matching data from dozens of catalogs. So the ZTF viewer is public. Please use it for ZTF data releases. And not only we have cross-matching with light curve data from Pan-STARRS and from Gaia, as well as alert data stream archive from Antares. But we also have some private space in this website. We used to write descriptions and apply text to our objects. So you see how it looks like for an expert. So we have some text here, we could write some description. And we, of course, we are not aimed to tag everything, all 4 billion light curves in ZTF data release. But what we are trying to do, we are trying to tag and write description to everything which were analyzed from our machine learning pipelines. So now we have something like 2,600 objects in this database. And, you know, it is pretty typical that we can find the same object from different methods. So, and we have a few experts and they can communicate through this too. Okay, let's go to machine learning stuff, to methods and to results. I will not describe algorithm today. You can refer to our papers for this, because today is not about algorithm, but more about results, about supernovae. So since we are interested in anomaly detection, let me describe a bit and use some definitions of anomaly and outlier, which are not the same as Dan just used. Sorry, Dan, but let me just use these definitions for this talk. So we said that outlier is something we could find is part of our feature space, while anomaly is something unusual astrophysical source, or unusual in terms of its properties, or just unusual for this data set. And anomaly definition for this experiment to this to current paper, to current analysis, is a subjective, and it is defined by experts, and it is absolutely fine, and I see no other way to do it, unfortunately, or fortunately, I don't know. So the first thing I will talk about applying this anomaly, machine learning for anomaly detection, for outlier detection, is our first analysis of just 3 fields of ZTF data with 3. So you see here is very small. It's actually a single CCD field of M31, normal size field inside galaxy disk, and one more field we call deep in this paper on high, having high galactic latitude. So the most interesting for today is probably deep field, but let me overview everything. So we had something like 2 million light curves in this data set, and we analyzed 227 outliers, and most of them were some bogus light curves, because I remind you there is no real bogus curve. So we have a lot of artifacts in our data set. So we even found Barcelona asteroid overlapping. You could see it here. But what is interesting, in deep field, our algorithm gave us 100 outliers from 400,000 objects. So anomaly detection, outlier detection in machine learning is unsupervised thing. Yes. So, and analyzing these 100 objects from 400,000, we found 6 supernova candidates, which is good result. I think, yeah, because if you select some random field on the sky and get all the light curve from there, then supernova probably will be anomalous, or at least outliers for this data set. And what is interesting, that only one of these 6 objects were in TNS. So we template fit them and tried to classify and reported everything to TNS. Okay, so next idea, okay, how we could remove these artifacts, remove the bogus light curves, and ask our algorithm to at least, maybe not to highlight supernova, but at least to dim, to make more important light curves we are not interested in. So here, active machine learning could help, and active anomaly detection. So the idea is quite straightforward. So we have, like in any active machine learning work, we have some initial model. We take the most anomalous, the best outlier from this machine, and ask our experts if it is anomaly or not, and if it's some boring artifact, our experts say no, please machine give me something better, or if it is good shiny supernova, we say machine give us more like this. And it is exactly what we try to do. So for technical implementation and performance tests, please see this paper. It is a bit methodological, but let's go to the results of for data release things. So here we already analyzed not single high galactic latitude field, but 70 fields. And you could see here that 35 of them, that fields in black frames, have some supernovae detected. So we took 30 best outliers from each field, totally 2,100, but there were some overlapping, so less unique objects, because you remember we have different objects in different fields in data releases. And among them, we found 105 supernova candidates, and some of them are not candidates. They are spectroscopically confirmed supernova found at TNS, but 57 of them have never been reported to TNS, so we consider them as newly detected probable supernovae. And what is interesting, something like 30% of these 57 have triggered no ZTF alerts, at least during the epoch of transients. So we again classified everything using plate fitting, and we also find some super-luminous supernova candidates. I'll talk about it a bit later. And it is still preliminary result, so we haven't submitted it yet. So some numbers could change in the future, but generally picture at this. Okay, what else can we do to find some missed supernovae in ZTF? Because at this point we understood that probably ZTF contains a lot of missed objects. Okay, sorry. Yeah, I see some messages in Zoom and thought that if it is from here, no, sorry. And we found accidentally that we could use a very simple approach to find more transients. If we have some non-transient or some good transient simulation, we could just look into Fisher space and find nearest neighbors, assuming that transients form some cluster in a Fisher space. And we did it with a bit different data set. It was GR ZTF data release for light curves. And initially we used SNAD simulations and found nearest neighbors to these 7 different simulations: super-luminous supernova 1A, 2, and TDs, and found 4 new supernovae. And then we just tried to use real ZTF objects as targets and analyze their neighbors. And at this moment we have something like 150 probable supernova, which hasn't been reported yet because we need to analyze it. So it is kind of preliminary result, but it is still a huge number. Okay, some probably interesting results. One probable supernova has a sister in its host galaxy, 15-year-old sister. One supernova we found is actually not our detection. It was detected by master in master network in GRB localization map. So it could be potentially afterglow, but of course we are not sure about it. Another interesting thing that we accidentally found a lot of bright M dwarf flares in high cadence data, and we are doing another paper about analyzing these M dwarf flare results. And most interesting that a bit preliminary result, but we found pretty good superluminous supernova candidates. So for example, this SNAD 160 published research note about it. You see template feeds that it is much broader than supernova templates, and it is more or less consistent, at least by the duration and luminosity, with superluminous supernova templates. And here our 3.5 new superluminous supernova candidates, half because we are not sure about this blue SNAD 121. And just for comparison, black dots are supernova 2006G Y, which is superluminous supernova type 2, redshifted to Z 0.3 and 0.4, just comparison to show you how broad our candidates are. Okay, the last slide before the summary. Why all these supernovae were mixed? So we actually don't have an answer to this question. Data releases, we analyzed data release 3 and 4, they included data from the first years of ZTF. So probably some of transient were missed just because survey was new. And for example, here you could see that some reference images was taken during early transients, yes, here in a LED stream from Antares, we see something like plateau, and which is going down here, but in data release, we see some transient or transient-like thing at least. And 20% of our new candidates have this issue, so that they have wrong reference magnitude. And something like 20% more, as I already said, are not presented at all at a LED stream. And probably it was an issue for another half, another 60%. It is an issue that the survey was young and Broca classifiers was not so strong. Yes, and it is we could see the same dynamics in ZTF bright transient survey, which is spectroscopical survey, comparing the first year and the second year of the survey. You see that at least the first half year, the detection rate was not high enough. So there probably should be something like 1,000 more missed supernova during the first year of ZTF. Maybe there are other reasons. So to understand it, we should go to later data releases and to try to find supernova there and compare how well we are in finding new missed supernova-like objects in new data releases. I think it is very important for LSST and for first years of LSST to understand what went wrong here in ZTF. Okay, I'm finishing with the conclusions. So we present few very powerful algorithms to find transients and to find anomalies, but it is another story. We detected 100, maybe 200 already. We should check probable supernovae, and among them a couple of very bright and broad super-luminous supernova candidates. We should think what we can do to avoid these problems with first years of the survey for LSST. And we're looking forward to find some interesting hour-long transients in high cadence data. It is what we are working on now. Thank you.
Thanks. We have time for 2 or 3 questions. After this, we have the break. So, yeah, fine. I don't see another. Dan, are you? Yeah.
So is there actually some way to integrate external modules like this into refit, or at least have you kinds of groups working together? Because it seems like you're giving us a recommendation system, and best could be find the most anomalous transient and follow that together. And it would be really helpful if there were APIs on both ends here from SNAD and from refit, where we could literally take these things like Lego blocks and actually fill them up, and maybe even take something like Andy's Storm Toolkit and trigger a follow-up of things like LCO after.
Did you hear that? Is it a question or comment?
I think it is a comment, yes. So I agree.
Yeah, I'm thinking about the chicken and egg problem here of if it doesn't show up in the alert stream in the first place and we want to try and do this in real time, how do you even know that you missed a thing if it's not in the alert stream? I can see how obviously going back later you can find it.
Yeah. So it's a very right question, and I don't know. Yes, and I think this could be a kind of problem. Yes, so we must understand if we really lose some data in ZTF. Yes, if it is not going through the pipeline and achieve alerts, yes, we must understand why it is happening and prevent it happening in the LSST, right? So we have this opportunity because now we have data releases, which is absolutely alternative pipeline and different photometry.
I mean, this, according to Rick, which always tells this in DES, you use fakes. They used fakes to figure out if they were missing things. But LSST, I don't know if that's something that's planned. I think not. Yeah. Questions, comment? Well, if not, thank you. Thank you again, Konstantin. We have a break.